Joseph had heard, right? Joey submitted his case study. What'd you do?
Actually, 4 times, like as far as like.
It looks so good.
I just, okay.
Jill should become our teacher.
All right, so we're gonna let it go.
No, you.
All right,
See, that's what I. Right.
so we left off last class talking about this uniform distribution. So we kind of had this density function, but I said, really, where does this come from? Well, we have a uniform distribution. It's kind of this equal probability across all possible outcomes in between a minimum and a maximum value. We said the height of this distribution, or this rectangle, will just be 1 over the range of possible values. So 1 over the maximum minus the minimum. At this point, now if we want the probability of being in between any two values, like let's say I'm here and I'm here, I'm just going to be looking for the area of rectangles. Right? So anytime I've got, maybe it helps to write it out this way. Right? So there's going to be two values that kind of tell me the start and the stop of whatever interval I'm interested in finding the probability of. Well, if the height is just 1 over max minus the min, then to find the area of this rectangle, I would take the height, 1 over max minus min, multiply it by the width. Well, the width is just wherever my interval ends and where it begins. So, I mean, this uniform distribution, I think, is pretty easy, especially if we draw it out and have that visual. We're just finding the area of rectangles. Right? Some summary statistics. If I want the mean, if everything's equally as likely, remember when I showed you another way to think about the mean was that everything was being weighted 1 over n. So in the original mean calculation, we're treating everything as though it's equally likely. If everything's equally likely in the uniform, all we really have to do is say, where's the middle point? Where's the middle point between the minimum and the maximum, right? So our mean will just be, I think I have it written a little bit different there on the slides, right? But you're just adding up the min and the max and dividing by 2. You're looking for that middle value. Okay? So what ends up being true about the, I'm going to draw this to scale. What ends up being true about the uniform is that the mean is actually also going to be equal to the median. It's a symmetric distribution. If I split this distribution exactly in half, it would fold on top of itself. So I've got a symmetric distribution. I can find the mean pretty easily. It's fairly intuitive. The variance is not intuitive. We've got an equation, kind of like the binomial. It always simplifies down to n times p times 1 minus p. Here for the uniform, it'll always simplify down to the range, right? D minus c represents the maximum minus the minimum. So it's going to be the range of that distribution squared divided by 12. Right? And that 12 comes from, you can like imagine like I'm dividing by 2 to get the mean. So then when I'm subtracting that and squaring it, like you can kind of imagine this number starts to kind of be doubled here and there. But if you really are interested, Google search uniform variance proof, and you can walk through the math line by line. But this is what it will always simplify down to. And it kind of makes sense, right? If the range of possible values we can see is wider, and they're all equally as likely, well, then our variance should go up. So if that range, maximize the minimum, gets bigger, so does our variance. Right? But that's really the only thing influencing our variance is the range of our values here. And then the standard deviation, once again, you're probably tired of hearing me say this, but it's just a square root. Any questions on this stuff? It shouldn't be too bad. So let's say we kind of did one example at the end of class to really highlight a specific point, but I've got demand for popcorn being uniformly distributed from 1 to 10 pounds. What would the mean pounds of popcorn demanded here be? I'm not going to use them for this one. It's too easy. Yeah. So this is where you have to be careful, right? Because for whatever reason, and it's very easy to make the mistake you just made. You look at these values, and it's very easy to quickly subtract them, right? Because in that variance equation, you're using the range, the difference between the minimum and the maximum. But for that mean equation, right, we're actually adding them up, right? So a good way to check, like, because like I said, like everyone makes that mistake. So yeah, even on the exam, a lot of times when I have the mean, it'll always end up like almost split sometimes in my regular sections. So what I think helps is to draw this out, because if I then want to plot my mean, if I were to think that I'm finding the exact middle point of the data and I write 4.5 down here, it like kind of right away, I'm like, wait, this looks like it's a lot closer to this side than it is to the other side. It should be exactly in the middle. Sure enough, I subtracted it. I was thinking of the variance. I actually needed to add those two up and divide by 2, which would have given me 5.5. Which, yeah, okay, that looks like it's a little bit more kind of in between the two. So the other thing I would say is tricky is if you ever have something that goes from a negative value to a positive value, right? Because this one choosing negative 10 and 10 makes it pretty easy. The middle value there should be automatically you should think of 0. If I add these two up, that's 0 divided by 2 is still 0, right? But if I think about, oh, I'm looking at the range here, and then I do that, I'm like, wait, 10. This one I could very quickly identify I made a mistake. But if it was something like -2 to 10, a lot of people might be kind of, I don't know, tricked into thinking like, okay, like I'll add these up, divide by 2, or I'll subtract this one, like you'll take 12 and divide it by 2, which what you actually should be doing is when I add these up, you should be taking 8 and dividing by 2. So I just be careful with negative signs. Maybe drawing out kind of helps you identify that number doesn't make sense given this minimum maximum. But yeah, for this one, we add them up, divide by 2, you should get 5.5. Any questions on that? So automatically, what's the probability that I see demand be greater than 5.5? Yeah, if it's a symmetric distribution, each side would be worth 1/2. And I can go through, use this as my A and B values, right? And I can plug things in, find the area of that rectangle. But automatically, I know for the uniform distribution, the mean splits it in half. So there's 0.5 to the left, 0.5 to the right. Because the area under this curve, this flat line is 1. This is an actual movie, by the way. I watched this when I was a kid. So there's like a couple other like great old Hulk Hogan movies that are, I mean, they're not good. They are laughably bad, but they're good in the sense that they're so bad that they're good. Oh, I don't know why this is actually, I think it's because I accidentally unplugged it. Every time I do kind of want to see where we're at here and get you guys recorded for being here today. Actually, scratch that. I don't want to do this today. Whatever. We'll have plenty of days. So I'd rather talk through this and go through more stuff. So we've got this, we want to find a product interval. I kind of walked through this earlier, how we can think about this. It's just the area of a rectangle, right? So let's say I have the same setup, but I want to know what's the probability that if the theater makes 9.5 pounds, that they're going to not have enough. Well, the only thing that would mean they don't have enough is if demand goes over 9.5 up to 10, right? So this is kind of a tricky one. I'm thinking about this in terms of a percentage as opposed to just the probability. It's a little bit tricky whenever my interval ends or begins with my maximum or minimum value. So notice here, I said the only amount of demand that they wouldn't have made enough for if they made 9.5 is anything above 9.5, but below 10, right? We're capped at 10. So now I've got my A value, my B value, right? The height of my rectangle, I plugged in 1 over minimum minus the maximum. So 1/9 multiplied by 10 minus 9.5. So this is going to be, what, 1/16, which I think is, no, 1/18, which is probably 5.6. Thinking about this in my head correctly, well, 0.056, and then as a percent, 5.6%. Is that right? Okay. I think that's 118. Any questions on this? I think these uniform ones are easy. Now, something I might do on the exam is something like this, where I might say, okay, what's the probability that demand is between 9.5 and 10, or in between 2 and 2.5. Right? So kind of like the union of those two things. Well, we're dealing with areas here, there's no intersections, right? So if I'm just looking for the unions here, it's just going to be the probability that's between 9.5 and 10, plus the probability that's between 2 and 2.5 pounds. So right away, you should be able to tell me what this answer is. Pretty quickly, at least. Yeah, so why did you know that?
Because, they're both 0.5 times 190.
Yeah, so if you calculated the area of this rectangle, you would have found exactly what you did before, but you don't even have to like go through and plug the values in, because the idea of the uniform distribution is every value is equally as likely. So if I'm looking at an interval of the same length, it's always going to have the same height. So automatically the area of that rectangle would have to be the same. So if I've got two intervals of the same length, I really only have to do one calculation and then like multiply it by 2. Right? Or add it to itself, however, whatever is easiest for you. So, we did that one in the last class with a probability that one value, we can prove that this uniform at least is 0. So I said it's true for all continuous random variables, at least up to this point, you can believe it. Right? So we start to look at more continuous random variables after these things. And that's kind of all that we have, right? So that's all we really need to do with the uniform is kind of find areas. And that kind of sets us up for some stuff we'll do with the normal distribution, which is what we'll start talking about after the first exam. So at this point, there's no questions on any of this. I'll kind of jump to the practice exams and start working through a few problems there. Yeah. Mm-hmm.
Is from the question, but like, where do you get the A and B from again?
This is a weird one, right? So let's say what's the probability that exactly 6 pounds are determined? A and B are the beginning and the ending of the interval I'm interested in. So if I'm looking at exactly 6, the beginning and the ending of my interval are the same thing. So this one's a little tricky in that my interval starts and stops at the same value. Does that answer? Any other questions? All right, so let me see here. I know I've got practice exams. So, oops, this is right. So one thing I would kind of just to talk about the exam a little bit, and we'll do some review, and then we'll do more review on Monday. Kind of really give you some more time to look at those practice exams, figure out some problems that you might be having difficulty with. But just some more general tips. So so I have it written. Let me see if I can remember off the top of my head. It was 18 multiple choice questions, all worth 4.5 points, which I think gives us 81. No, is that right? I think so. And then 4 kind of short answer, which is basically like short answer is you're working through a problem and just showing me your work to get to the answer, right? I'm just not giving you 4 options. So you know, any multiple choice question that I put in those practice exams, I could easily just turn it into a short answer by deleting the answers that I'm showing you, right? Like that's all I mean by short answer there. Like, it's not like I'm going to ask you definitional stuff. If you're working through some of these problems and just showing your work so I can give partial credit. So those are worth 5 points each for a total of 20. So the total number of points is 101, and I'll just grade out of 100. So everybody starts out with 1%. Just so I don't have to make the multiple choice worth like these weird decimals, right? I can just kind of give you an extra point. That was very lazy on my part, but there we are, right? So So that's kind of the makeup of the exam. I would say those practice exams, at least in terms of the types of questions they're asking, would be very good templates to look at. Probably practice exam A a little bit more than practice exam B. And someone asked, did you ask me to get up a more detailed one? Was that this class? Nobody asked me that? Okay, that must have been for my regular sections. I've got another exam. I think it's good to go over. And it will have like more detailed answers, kind of like this one does, like with the actual formulas. I'll throw that up after class. I don't want to like overwhelm you where you feel like you have to go through all 3 practice exams. It's just another one up there. If for whatever reason, when you're looking at practice exam A and B, if it helps you to see how they were worked out on practice exam A, I don't have the answers pulled up, but I think that they're just, they're just an Excel file with what the letter was, right? So that's not quite as helpful. So I'm going to put up another one, practice exam C, and it'll be more like practice exam B, where I have it worked at what the answers are kind of typed out in a Word document, just to kind of give you, if that's a little bit more helpful. Other than that, so you'll have this formula sheet. What I would do if it was me is I would print this formula sheet out, right? And then I would write next to it, this is mean. This is sample mean. This is population variance. Now, when it comes to taking the exam in class, I'm going to give you a formula sheet, right? So you can't because otherwise I got to worry about people writing on the back. I got to worry about some people are writing more than others. I kind of want everyone to just be starting off with the exact same amount of information on these formula sheets, right? But if you've been studying with this, so once you write down kind of what all these formulas are, like have the word next to it, if you're using that while you're studying, as soon as you get that formula sheet, what I would do is then start to write out the ones that I know that I sometimes forget or I have a hard time with, right? And, that way I can kind of start out, and even if I don't write it down, just the fact of using it while you have what each equation represents next to it, builds that into your memory. I hopefully it doesn't, but I think maybe it sounds dumb, but it really does help to remember things if you do that. Even though I'm not going to have this on the exam, just having seen that word next to that equation so many times studying, it's much easier to remember once I get to the exam. So that would be a suggestion that I would make that I think has helped people out in this class in the past. Also, don't miss out that there's a second page to this formula sheet. So when I print it out, there will be a front and back side. The uniform distribution equations will be on the back. Okay, so that's just our mean, our variance, and then that density function, which I honestly think it's easier to draw the visual and find the area of a rectangle, but there we go. Any questions related to the exam or anything before we kind of start picking and choosing a couple problems here? No? Yeah.
What do you think is the most useful practice exam out of the 3?
Probably the one I have up there that's I believe practice exam B, right? Or no? Oh, this is the one that I didn't give you the answers for though, right? Hold on. Yeah. Of A and B, I would say it's going to look a little bit more like practice exam A. Practice exam A is useful because it has it more the problems worked out. But I would say the way that it's phrased and kind of that practice exam A is a little bit more like how I'll write this one. I had to choose one. Then C will probably be kind of somewhere in between those two, just because it has it worked out. It will look a little bit more like the exam than practice exam B would. Any other questions? All right, so if you had to choose, what subject or topics do you think is probably the most difficult, or would you are any of you have any issues with any of the material that we covered that you really just hate these one types of problems? probability, like contingency tables, Bayes theorem, binomial distributions. You don't have a problem with any of it. Yeah. Okay. I think the Bayes ones, in my experience and personal opinion, I think are the most difficult. So I'm going to hit enter a bunch of times here so we don't have to keep going between pages. And then going to zoom in here. And on practice exam A, since you only have that Excel file that shows you the answers, this will be some good ones for us to work through as well. So let's start out with all this information about steroid use and baseball and got what? So major concerns, a manufacturer claims the probability its drug test will show positive, given that an athlete uses steroids. So this is an example where practice exam A, I'd probably write it more like this than I would here. I'm using this terminology of given. So given that the athlete is not using, so given that they're not using, the probability that we get a positive test result, excuse me, the test is equal to positive, is 0.95. And then the probability the drug test shows positive given the athlete is not using. Wait, did I read that wrong? I did. The first one we're told is using, right? So given that they're using, right, the probability they test positive is 0.95. However, given that they're not using, the probability that we get what a positive test result is 0.01. And then a recent article suggests that if we choose a player at random, the probability they're using steroids is 0.15. So probability that they're using is 0.15. So I could start out and I don't have to do anything else and I can start to try to answer these questions, but there could be missing components that I don't have. So I would personally try to figure out what those missing components are ahead of time and then jump into them. But I'll show you what would happen if we didn't do that first, right? We just take the probabilities we're given and we try to start solving for these, right? So the first one is, what's the probability that an athlete uses and tests positive? So we've got the probability that they're using and test comes back positive. So I'll show you where in the formula sheet in just a second this is, right? But anytime we want the intersection of two events, it's going to be the conditional probability divided by what we're conditioning on. So this one's a little tricky, right? And actually, even the way I would write the exam, I'll probably get a little bit tinier than this. So if I try to write this out, right? And here's my event A, here's my event B. I go to my formula sheet. Somewhere, there we go. And I say, okay, here's some of the probability. Okay, the intersection of two events is the conditional probability times what I'm conditioning on. Okay, so probably help if I made this a little bit bigger. Okay. So we've got the intersection of the conditional probability. So my event B is that the test comes back positive, given my event A is that they're using, right? And I divide that by the probability of whatever I'm, or actually, sorry, the probability of whatever I'm conditioning on, which here I'm conditioning on the fact that they are using. So notice here, the intersection of two events, the conditional probability multiplied by, oh, I have this backwards too, because we're not solving for sorry. I ran out of room. I'm multiplying by the probability of whatever I'm conditioning on, right? So that was the probability. I was just writing down there because I ran out of room, not because I had to find it. Okay. Let's look at the general form of the equation. This wrote out in the context of our example. given that someone's using, what's the probability they test positive? I think I have that over there. I think it was 0.95. Probability that someone's using is 0.15, right? So this is 0.14 something probably. 1425. So 1425. I think on the answer key around the things to the third decimal, so probably 1.143. Any questions on that one? We're just kind of building up here to a Bayes theorem problem, right? So the next one is going to be something that's very similar. Right, so now I want the probability that an athlete who's not using steroids and test positive. So I'm not going to go through this one just for the sake of time, and I think there's better uses, but everything's going to be exactly the same. Right? Except for now we're just looking at not using it and testing positive. So if I do that, probably that someone tests positive given they're not using was 0.01, I believe. Well, now here's the first time where if I wanted the probability someone's not using, what would it be? Yeah, so I wasn't directly given it, but I know that there's only two true states of nature. Someone's either using or they're not. So those two have to add up to 1. So automatically I know the probability that someone's not using 0.85. Right? So this would be what? 0.0. 0.0085, right? So pretty small. Okay. So the next problem asks us, given that the test comes back positive, what's the probability the athlete is not using steroids? So here's where it gets a little bit tricky. Okay. So first of all, we're okay with everything up here. So remember, ultimately what this represented was probability that someone was not using and the test came back positive. This represented the probability that someone was using and the test came back positive. So it's kind of like if we added these together, this would represent every single person who tests positive, right? Those who tested positive and were using, and those who tested positive and were not. So before we even think about Bayes' theorem here, if I asked you, I said, okay, given that the test comes back positive, what's the probability someone is actually, did I say using or not using? Not using. Yep. So really what that's saying is, out of everyone who gets a positive test result, what's the probability that they're not using? So take the number of people not using who got a positive test result divided by just the total number of people who got a positive test result. Well, what did we just say? If we add these together, that's everyone who's ever got a positive test result. That would be our denominator. What would our numerator be? It would just be people who are not using and got a positive test result. So really all I'm going to do here is 0.0085 divided by 0.0085 plus 1425. But I had all that work done ahead of time. And I hadn't asked you those leading questions. What you're going to have to do here is use Bayes' theorem, but write it out in the context of your example. So if we go to that formula sheet, we've got Bayes' theorem right here. So this is kind of where, if I've got the intersections, I could plug those right in. That's what I found in the previous two problems. The same outcome of the test, but here the intersection of that outcome of the test and the first state of nature, add that to the outcome of the same outcome of the test and the second state of nature. So I, here, if I wanted to, if I didn't have those previous two problems done, I could just write out that longer Bayes theorem in the context of my example. So my S is not using, my E is seeing a positive test result. So not using times the probability I see a positive test result. Given that someone's not using, first part of my denominator is the exact same as my numerator. So I could write this out, but I'm going to run out of room if I do. So Imagine it's going to be the exact same thing here. Plus the probability of what? S2 or S comp, right up there. S complement. So if my S is not using, S complement would just be that I am using, times the probability of E, which is that the test comes back positive, given S complement, which we just said was using. So now I'm just going to start plugging things in. What's the probability someone's not using from over there? Is that the 0.85? Times the probability that given they're not using, what's the probability the test comes back positive? 0.01. First part of my denominator is the exact same as my numerator. What's the probability someone's using? Not 0.05, but 0.15. Given that they're using, what's the probability the test comes back positive? Is it 0.95? No. Oh yeah, this times 0.95. But notice, that's exactly what I was really doing in the previous two problems. I was finding those intersections, which is really what these components represent, right? They all represent. It's just kind of different ways of thinking about the same thing. Any questions on that one? So what if instead I had that I wanted to know, given that the test comes back negative? So now everywhere I had a positive, I'm running negative. Well, now I don't have these probabilities. I look over there, do I have the probability that given someone's using the test comes back negative? No, but what could I have done? If I condition on the same state of nature, but I look at the other outcome of the test, what should these probabilities add up to? 1, right? Given that I'm looking at only people who are using, they either get a positive test result or they don't. So I actually have this, and if I condition on the other state of nature here, not using, but I look at the other outcome of the test, I know these two have to add up to 1. So I get 0.99. And now I could actually solve for something like that. This was just an example where you didn't have to. It was kind of nice on this one. Could have been a lot more mean, I guess I should say. Any other questions on this one? So I think part of it is identifying the steps for me, identify what information we're given. I would probably come up with the missing pieces if it was me right away. Then write down what you're looking for. Right? We wrote down the probability of what we're looking for. This is your S. This is your E that you can line up or match up with the general form of the equation. Now it's just writing out this equation in the context of your example. After that, it's just plugging in those probabilities that you identified earlier into that equation that's written out in the context of the example. All right. So let me see. These ones are pretty easy. Oh, it looks like I did put in some of the work on this, did I? Not all, and not the best example, but oh, okay. Let's do this one. I might come up with some additional questions. So let's say 40% of credit card company or credit card consumers carry a balance from month to month, and we interview 10 credit card companies. What's the expected number of customers and the variance? Okay, so let's start out with that. So here, I'm looking at the underlying probability of success, 40%, so 0.4. And I'm looking at 10 consumers or customers, so my number of trials is 10. Okay. If I want to come up with the expected value or the mean and the variance, I'm going to go to my formula sheet. And here's my binomial equations, right? So if I had the formula sheet printed out, next to here, I would write like binomial, right? This is my probability function, mean, variance, standard deviation. So from here, it's a matter of plugging our values in, right? Our n was 10, our p was 0.4, so our mean is going to be 4, right? Variance, 10 times 0.4 times 1 minus 0.4. So there I've got what, 4 times 0.6, so 2.4, I think. Okay. So it's really just a matter of, once we identify this as a binomial distribution setup, someone either carries a balance on their credit card or they don't. The underlying probability of success is the same across all customers, and I'm capped at the number of customers I could see carry balance, which was 10. So then I identify the binomial mean and variance equation, plug my values in, and I'm done. So that should be like an easy question. Probably I would like combine that question on the exam, like here's the setup, what's the mean and variance for this, whatever variable I'm looking at. So I would kind of have like two questions into one. But then maybe what's more interesting is what would be the probability that exactly 4 customers carry a balance here. Okay. So go back to our formula sheet, right? So this is the equation that we're going to use. Right? I might do something like this. I'm just going to write it out and hopefully see how we can maybe make this a little bit easier. So if I was working through this one, this is how I would do it. So n, well, I'll write over here. N was 10. We're interested in 4 successes, and the probability of success is 0.4. So n factorial, so 10 factorial, divided by x factorial, so 4 factorial, and minus x factorial. The probability of success, 0.4 to the x power, so 0.4 to the 4th. And then 1 minus that probability of success, so 1 minus 0.4 to the n minus x, which is 10 minus 4. Well, right away, I would just replace this with like, that's 0.6 to the 6th. I can do this math in my head. So then what I would do is in my calculator, type in 0.4 to the 4th times 0.6 to the 6th, right? Whatever that value is, I would write that number down. So I don't know what that is off the top of my head, but let's see if Excel will help me out here. So equals 0.4 to the 4th. I don't want to do parentheses, so I'm going to be lazy here. So 0.001194. No, just 1 more, right? Oh, all right, you're right. That's weird. Okay, that's weird when this angle doesn't come out. So now I just need to figure out what this component is. So, I could, hopefully, if I found that factorial button in my calculator at this point. If I hadn't, right, and I just think about writing this out. Right, so 4 times 3 times 2 times 1. 10 minus 4 is 6. So 6 times 5 times 4 times 3 times 2 times 1. Everything past 6 cancels. And I'm just left with 10 times 9 times 8 times 7. So here I could do this on Excel. 10 times 9 times 8 times 7. And then divide that by 4 times 3 times 2 times 1. Right? So this ends up being 210. Now it's just 210 times 0.001194. Okay. So we'll do that. And we get approximately 0.25, right? If I'm rounding to that second decimal, this is going to be 0.25. So I'm just using Excel as my calculator. I wasn't trying to use any built-in functions or anything. I'm just using it as a calculator, which probably helps, still helps though if I zoom in. So all I did was kind of break things down by parts there. Okay. Any questions on that? Yeah.
Is this question on paper or is it?
So it's on paper, right?
Okay, okay.
So you can't use that binomial distribution function in class and exam because I don't have computers in this classroom, right? I wish I did. I'd make the exam harder and make you use Excel stuff. I actually don't know if it'll be better for you or not, but So we're gonna have to be able to kind of do this by hand, right? Or by calculator, right?
I just wanted to go with it.
Yeah.
What? No, I was confused with finance.
What do you do?
No, you see.
All right. Sabotage over here. So we end up with about 0.25, right? I'll often do something like this as well. So what's the probability that at least one customer carries a balance, right? So if we want the probability that at least one customer carries a balance, what are we really saying there? In terms of probabilities, that would be the probability that X is, yeah, 1 or more, or greater than or equal to 1. Right? At least one customer, right? 1 or higher. The problem is, on an exam with limited time, what values fit this criteria? X could be 1, plus the probability X is equal to 2, plus probability X is equal to 3, all the way up to 10. It's going to take a hot second. I probably don't expect you to do that. But if we think about this is our event A, what's another way that we could solve for this? Not just the complement, taking the complement and yeah. So subtracting it from 1. We're probably just implying that, but I want to make sure that I say it correctly just in case. So what would the complement be here of X being greater than or equal to 1? X just being less than 1, or the only thing that would actually fit that criteria would be the probability that X is equal to 0, right? Being less than 1, we're still dealing with a discrete random variable. Only the first outcome we could see would be 0. Now it's just a matter of plugging in that in. And here a lot of stuff becomes easy, right? So like n factorial over x factorial and minus x factorial probability of success to the x times 1 minus the probability of success to the n minus x. Well, notice 0 factorial is 1. I can ignore that. 10 minus 0, 10 factorial over 10 factorial cancels. This whole guy right here is just 1. Anytime I have as x is equal to 0, this will always be 1. Anything to the 0 power, it's just 1. So really all I have to do here is 0.6 to the 10. That's going to be my answer. Well, almost, right? That's the probability x is equal to 0. I then need to plug that in and subtract it from 1 to get what I originally. And if I had forgotten to do that, so I don't know if, so this is probably approximately 0.01 here. So maybe I look at the answers and I answer 0.01. This is where don't get too lost in the formulas. If I was actually looking at this one ahead of time, before actually using the calculator, if I'm doing this by hand, I'm crossing off B right away. Because what would be the expected value? We already came up with it earlier. We said it was 10 times 0.4. So on average, out of 10, 4 customers would carry a balance. So 4 should have a pretty high probability of occurring. And then 3 and 5 will be a little bit less likely, but still fairly likely. 2 and 6 falling off in probabilities, right? Here, I'm trying to find a probability X is 1 or greater. That includes the most common outcome of 4, but it also includes every outcome other than 0. So that probability should be pretty close to 1. Like before I even start thinking about what formula to use, just think about the context of this example. 0.01 here makes no sense. In fact, 0.58 seems too low to make any sense. I'm thinking it's got to be at least as high as like 0.9, right? So A and C is really the only answer, even if I can guess that I should be going with, just thinking about the principle of what I'm looking for, right? So a lot of times, thinking of that kind of stuff ahead of time and crossing off answers that you know just don't make any sense for this, right, prevents you from making really easy mistakes like, okay, I got the calculation and finding 0.01 is the answer. Well, I forgot it was started way up here and I had to subtract from 1, right? So a lot of times you can prevent yourself from making these easy mistakes if you just think about like, what range about would this answer be? I'm just kind of thinking through a little bit. I don't know. It's not getting too lost in the formulas, I think helps. Any questions on that? Is that clear? Or I'm saying, I'm seeing most people nod. What's something else I might do in this exam? So one thing I would say is I believe this exam doesn't have any Poisson distribution questions on it. I can tell you on the exam there will be, right? So there will be questions over the binomial, the Poisson, and the uniform distribution. So there weren't any on this practice exam that had the Poisson. The additional one I post should have some. If you're looking for problems of that to work on, that would be a good one. It would be good to look at that third exam on the post. Yeah.
So we'll be able to know that that is that formula because of any of this average. Or
So
will we, like, because I'm just concerned that I will get them
mixed up. So the easiest way to identify differences in the Poisson and binomial is binomial distribution. If you want to think about like our cap, right? You know, you can give me a number for the highest number of successes you could see in a binomial distribution example. Like this one, the most people you can see carry a balance out of 10 is 10. The Poisson distribution examples, if you think about what's the highest possible number of successes I could see here, it's going to be like it'll be like the number or the population in that country. You know, like there's not really going to be a value that you could say would be the highest number of successes you could see. That's probably the best way to identify the difference. Also, for a Poisson distribution, we have to be thinking about some time frame. So this is something like, 8 car crashes. The average number of car crashes we see every week is something like 8, right? So you're going to have to be given an average. It's going to be the average over a certain time interval, and you can't really put a cap on it. That's when you know you're dealing with a Poisson distribution as opposed to binomial. And I'll bring, even if we don't get to it Monday, I'll bring in some Poisson examples, especially one where we have to change the interval. So what we did on Wednesday, I showed you an example where we had to change like from a week to a day or whatever it was, a year to a month. I'll go through another example like that on Monday for sure, because I wrote the exam, so I think it'd probably be good to know that. Yeah. Okay.
I just wondered, didn't you not? Do you know?
Yeah, was there a typo in that one?
I'm not sure. I mean, I guess that was.
Yeah, it definitely is, right? If X is greater than 3 million, that should just be 0.4 here, right? So this only makes sense if I had that, right? Yeah, thanks for pointing that out. I will re-upload this practice exam so that it has that change. I probably just read it quickly when I was typing in those answers and didn't pick up that it wasn't inequality. Any other kind of quick questions? We kind of ran out, a couple minutes left, but we kind of start a batch of questions. I want to make sure if we do the contingency table stuff, we keep that together, and the Poisson stuff, keep that together. Yeah.
I had a quick question about like standard deviation, just like the normal thing. So I kind of have it like, so like you have X and then X minus the square.
Yep.
And then do you divide that by the number?
Yeah, so this is where, when we're looking at a standard deviation, if it's a population data set, then we divide by the number of numbers that you had, right? Or the number of deviations you had. If you're given something like a sample data set, then you would take the number of observations minus 1, right? I think most often I'll give you sample data. So usually we'll have to be doing that n minus 1. But kind of notice how in this exam, I told you, this is sample data bold and underlined, right? So you know that if I'm calculating variances and standard deviations here, they're going to be sample variances and sample standard deviations. And I try to do things like that when there's like bold and highlight things that are important. Right? Any other questions? Before. All right, so we keep doing some exam review on Monday. At least based off your responses, I'm thinking that this exam will go pretty well for a lot of you. If you have any questions, feel free to reach out, especially next week. If you want to meet Monday or Tuesday, not during my scheduled office hours, reach out to me. We can find a time to meet up. Okay. All right. You guys have a good weekend and I will see you on Monday.